Okay, I finished drawing my inverse. Right when the camera stopped, I realized I had plotted the point 8, -2 instead of 6, -2. So I just took all the points that are in black and I switched them around, or excuse me, yes, in black. So -2, 6. So when I switch that around, that's 6, -2. And then I found another point that was 0, 3.5. So I went over here. Excuse me, and plotted 3.5, 0. This point is 2.5, 0. So I went and plotted 0, 2.5, because remember the definition of inverse is just switch your x's and y's around. And then last, this point was 3, -1. So I went here and did -1, 3. So then I connected it. And as I said earlier in the lesson, they're always symmetric about the line y equals x, which is the line that cuts the coordinate plane in half. And you can see this side is reflected on this side. This side is reflected on this side. So they're reflections. So the black line here is a reflection of this red line. The red line here is the reflection of that black line. So that's what inverses look like on a graph. So they're mirror images across the line y equals x. That's kind of cool, right? And we're going to do another one later, but I thought that would be a fun one to do. Okay, so let's go ahead and look at the second one. So is this going to pass the vertical line test? No way. It hits a circle in 2 locations, so that means it is not a function. And if it's not a function, it can't be a one-to-one function, which is a specialized kind, so just stop. If it fails the vertical line test, you stop. Okay, what about this one? Does this one pass the vertical line test? Yes, it does, because these never overlap. That one stops at 1, this one stops at 2. So it is a function. But does it pass the horizontal line test? No, it doesn't. Just think, if I drew this horizontal line right here, how many times do I touch it? Way more than one, an infinite number of times. So although this one is a function, that means all the x's are different, all the y's are not different. You can see -1, what is that, 5? Yeah, 5, -2, 5, -3, 5, -4, 5, -5, 5. So there's a bunch of points with the coordinate 5 on that graph. So that one does not have an inverse. Although it is a function, it's not a one-to-one function, so we would not be able to do this on the graph. What it means is if you did switch all the points around, they would not be mirror images. So that's what we mean, because I know you're thinking, well, I can switch the points around anytime I want, but they won't fit this description where they're mirror images across the line y equals x. And this one's not even a function at the beginning, so we don't even have to look at that. Okay, so inverse functions, one-to-one functions, their x's and y's are turned around, and to test them on the graph, they have to pass both the vertical line test and the horizontal line test. If they fail either one, they're not one-to-one. So here is the official definition of an inverse function. So if you have the order pairs x, y, the inverse function is designated as f inverse, and it's made up as the set of points y, x. So we kind of had that description earlier, but this is the official one. So if f is a bunch of points x, y in an order pair, then f inverse, or the inverse of f, is all the points with the coordinates switched around, y, x. And knowing that definition is going to be very helpful to you later, because we're going to be deriving the inverse function, and you need to know switch x and y around. I put that on the final exam, so that's important. Okay, so it says if f is a one-to-one function, Okay, so now let's see, write the inverse of each function. So first we have to make sure it's a function. -3, -2, 4, 11. Yes, it's a function. So now we can write our inverse and use your proper notation. F inverse equals, use your set symbols, and then just flip each point around. So 4, -3, comma, 7, -2, comma, 8, 4, comma, and -1, 11. So if you don't use the proper notation on connect, it will count them wrong. So make sure there's a comma between each point and make sure you have each of them in their set symbols. Use the proper notation. If this is F inverse. So G, we have 0, 1, 2, 3. So it's a function. That means it has an inverse. So G inverse, or inverse of G, is going to be, switch that point around, whoa, it's still 0, 0. Switch that point around, whoa, still 1, 1. Still 2, 2. Still 3, 3. So do you know what that means? This function is its own inverse. So when you go to draw the inverse, they would lie right on top of each other. And do you know why? All those points are on this line. So if an inverse is described as a reflection about this line, well, if all the points lie on the line, they reflect on top of themselves. So that's what this is. If you look, 0, 0, yep, right there. 1, 1, yep, right there. 2, 2, yep, right there. So all those points would be on that orange line, and that's why they would be their own inverse. So that's possible. You can have that. A function being its own inverse. I mean, there's only one such function, but yes, it's definitely possible. So when you flip the coordinates around, you get the same function as before. So that means it reflects right on top of itself. So the main thing is make sure you're using the proper notation, your set symbols, comma after each order pair. Okay, so this is what I was telling you about earlier. There's a special property about inverse functions that when you do the compositions, remember how we plugged G into F and we plugged F into G? So we wrote it like this. And then in the last lesson, I had you cross G of X out and write what it was equal to. Then we plugged it into F. Well, instead of getting two different answers like we did, we will get X each time, which is pretty crazy. I'm going to see if I can find our lesson from last time. Okay, so I want you to see the difference in the answers. So here's one that we did in our last lesson. So here was f of g of x, and here was g of f of x. See how they're not even the same, not close. And then if you look at the one below it, here's f of g of x, here's g of f of x. So they're similar, but not the same. Well, what this is telling you in this little box is that the inverse, when you take f of g of x of two inverse functions, or g of f of x, you don't get those big ugly things. You just get x. That's it. Just x. So let's see what that looks like. I'll put my notes away. So f of g of x, oops, switch colors, is always going to be x. And g of f of x will be x. And you do this in your next class, so you do have to remember these rules. When they're inverses, when you do their composition, each of them will give you x. If only one gives you x, then they're not inverses. If they both give you x, then they are inverses. So let's see what that looks like. It says show their inverses. So these are the two things I need to show. I need to show when I plug G into F, I get X, and when I plug F into G, I get X. So let's write f of g of x and do it just like we did on the last section. So we're going to take g of x out, move up a little bit, and we're going to do exactly what we did before, replace it with what it's equal to. So to find this first composition, I need to take function f. Wherever I see an x, I need to plug in 4x minus 8. So right there, I need to plug in 4x minus 8. And watch this magic that happens. I love this. It's pretty fun stuff. So 4x minus 8 plus 8 over 4. So watch the magic. Negative 8, positive 8, 0. 4x over 4, ding! Look what I get. I told you it was going to be magic. So everything undoes each other. That's why they're called inverses. Inverses are opposite operations: multiplication, division, addition, subtraction. So because these two functions are inverses, and remember what that means, when I graph them on a coordinate plane, they're going to be mirror images about that line. So that's what inverses are. So whenever you do the composition of inverses, they're going to undo each other all the way down the line, and you just get x. But when they ask you in 150 to show that they're inverses, you have to show both. Just showing f of g of x is not enough, because according to this, and that means they both have to give you x. So that means I still need to do g of f of x. Slide up just a little bit. So let's go ahead and do g of f of x. So g of f of x. Now if I can show they're both equal to x, then I've proven that they are inverses. So again, take your f of x out and replace it with what it's equal to. So this time f of x is x plus 8 over 4. So that's what I'm going to put in place of f of x, because they're the same thing. So what I'll be finding on this problem is, in function g, take out your x, and wherever you see an x, replace it with x plus 8 over 4. Okay, so that's exactly how we learned to do compositions in the last section. We write them as nested parentheses, take the inner function out, replace it with what it's equal to, and then you evaluate the outer function at that. So that means go into g. Wherever you see an x, plug in x plus 8 over 4. And it is a quantity, so it needs to be in parentheses. So we do 4x plus 8 over 4. So I took the x out, I put this in its place, and then minus 8. And watch this. Ding, ding. Nice. Remember how I said inverses undo each other? Well, timesing by 4 and dividing by 4 are opposites. We learned that 4 divided by 4 is 1. So what do I have left? X plus 8 minus 8. Ding, ding. There we are. So I have just shown that those two functions are inverses, because when I did f of g of x and g of f of x, they both gave me x, which according to this property, if they both give me x, then the functions are inverses. Cool, huh? Okay, we have one more. So if you want, and this is what I would recommend, why don't you turn off the video and do this one on your own? And actually, we only have 15 seconds left, so why don't you do this one now before you watch the next video, and then we can compare answers when we come back. Okay? See you in a bit.